Hi, this is Lut Maliki, and I'd like to talk to you today about ultra-low noise semiconductor lasers and with respect to their noise and applications and how the noise performance of these lasers impact the performance of the application. So we are familiar with the variety of areas where semiconductor lasers are used. They range anything from LIDAR to satellite communications, microwave photonics, atomic clocks, metrology, and frequency comb, and a large number of other applications. And in most of these applications, the noise of the laser is of interest. Now, when we talk about the noise of the laser, in the laser community, typically the idea of line width is used. Line width is a notion that was introduced by Art Schawlow and Schawlow-Townes in their seminal paper, and is demonstrated, is depicted by this delta nu. And later on, it was modified for the case of the semiconductor laser to have this line width enhancement factor that was introduced by Henry. And while these equations give insight into the performance of the laser, and they have some certain parameters that are fundamental to the laser included in them, the use of line width to depict the noise of the laser is really not very convenient, mainly because, number one, it is a simple and single parameter. And because it's a single parameter, it doesn't give insight as to how else the laser noise can impact the performance of in an application. And furthermore, associated with line width is the bandwidth within which that line width was measured. And if that's not given, it's very difficult to compare the performance of one laser with respect to another. Meanwhile, there are some emerging applications that demand really very high performance from the laser. And they range anything from higher resolution spectroscopy, millimeter wave RF photonics, and all the way to coherent communications, atomic clocks, and quantum logic. Now, typically, take the case of coherent communications, the low noise of the LO, which is of importance, has been given by the line width of the laser. And turns out that low noise of that line width is actually can be managed by signal processing and is not so much of interest. But recently, it's been demonstrated that for high throughput coherent communications, what is required is attention to be paid to the so-called 1/f noise of the laser. So what is that? Well, it turns out that if we depict the noise of the laser by power spectral density of the frequency fluctuations in this case versus its Fourier frequency, it turns out that we can get insight into what the type of the noise is and how it impacts the performance. For example, when we talk about the line width of the laser, typically we're talking about this wide frequency noise region, which is called white because it doesn't change as the frequency changes, it's flat. But when you go to these other regions, they have different slopes, and each one of these slopes is indicative of some underlying phenomenology that's going on with the laser operation, including, importantly, some technical noise due to, for example, vibration or temperature, etc. The spectrum of the laser, noise of the laser, shown as the power spectral density of phase noise, frequency noise, is given in the units of hertz over root hertz or hertz square over hertz. And while these are funny sounding units, but they're obviously very simply related to each other. And you can see that the line width of a laser such as this, for example, by looking at where the flat region hits the axis, y-axis, we can say this is sub-hertz. So one hertz would be here. Obviously, there is a relationship between phase and frequency, and this can be used to also depict the noise of the laser in terms of power spectral density of the phase noise. This is a parameter which is commonly used in the electronics community in describing and characterizing noise of oscillators. The advantage of using the phase noise is that you can get even more insight into what's going on with the laser and consequently how it can possibly impact the particular application and performance. For example, in the white noise region of the phase noise, you get typically, if there's no other noise, you get the shot noise. But if there's amplitude noise in the laser, then that amplitude, that is power fluctuations at the photodetector, convert to phase noise, and they mask the shot noise. And so they indicate a larger noise level than the shot noise could give us. So typically people increase the noise of the laser in order to suppress the shot noise. But turns out that if RIN is present there, that's going to keep the laser from operating at the shot noise limit. And that's an important piece of information that can impact the performance of a variety of applications, such as, for example, in LIDAR, in frequency modulated LIDAR. Now, how do we stabilize or reduce the noise of a semiconductor laser? Typically, that's done by locking it to an external cavity. And by extending the length of the cavity, essentially by having an external cavity, we improve the performance of the laser. The noise of the laser is suppressed. This is an example of a cavity which is really a piece of art made out of silicon, and it was designed very carefully to be suspended very carefully and put in vacuum so that it can operate and yield such low noise as 10 millihertz with a semiconductor laser. And that's really a record and very impressive. But turns out, of course, the price for this is that you have a complex system that operates under vacuum and requires power for operation, et cetera. And that is sort of not quite consistent with the desirable features of semiconductor lasers that include small size and small power consumption. To address this issue, OEwaves, for many years, we've been operating with the usage of these crystalline whispering gallery mode resonators. These are millimeter scale resonators made with highly transparent materials such as calcium fluoride and magnesium fluoride that then can yield quality factors that are as good as any other system at any temperature. And they operate, and these systems, of course, operate at room temperature. And Q being so high means that the line width of the mode is very narrow, the bandwidth of the mode is narrow, and that allows suppressing the noise by filtering it. And the way we implement that in our lasers is that we get any semiconductor laser that emits within the transparency region of this particular material that the whispering gallery mode is made of, and couple light into it. Some of the light goes out, but some within the cavity actually scatters back into the laser, and injection locks. And this self-injection locking system is very effective, despite the fact that it's very simple. It can suppress the noise of the laser by 60 dB, or 6 orders of magnitude. And this was something that many years ago we introduced and patented at JPL. Now, aside from the line width, there are other features of lasers that are of interest, and they include the ability to have this kind of a performance in any region of UV or IR, ability to have high usable output power, small size and power consumption, and operation that is robust under any environment that includes space or air or laboratory environment. And finally, it can be modulated, and its modulation is achieved under low residual amplitude modulation, RAM level. At OEwaves, we have lasers that satisfy all this. We can not only produce sub-Hertz line width, but importantly, the smallest 1/f noise of any laser in this kind of a small package. Custom lasers that range from UV to 4.5 micron in wavelength, and PZT for low RAM operation. We have demonstrated these lasers at UV at 370 nanometer by injection locking a Fabry-Perot laser. We have delivered to customers blue lasers at 446 nanometer for pumping lithium ions. We have delivered lasers for 795 nanometer. And because of the very low RAM, turns out that you can stabilize these lasers to transitions in rubidium and achieve this outstanding performance in terms of stability. This shows that by having low phase noise in the laser, we can achieve the very high performance in atomic clocks, and that's of particular importance in quantum technology applications. This is a laser at 2 micron, which was used for a airborne LIDAR for Air Force. And finally, a laser at 4.5 micron, which was used for very high resolution spectroscopy of CO2. Now, because the material that we use are very robust and very small, they are also robust against any vibration, and they can operate in high vibration environment without much impact. And this therefore makes them suitable for applications such as those in the space, among others. So in conclusion, I like to emphasize that at OEwaves, we deliver lasers which have exceptionally good noise performance with not only sub-Hertz line width, but also importantly, small 1/f noise. They have low RIN, they have low residual amplitude modulation for PZT, for locking. They can deliver very high powers depending on the wavelength. They're insensitive to environmental vibrations, and there's option to even hermetically seal them. They are GUI controlled, and they have control ports for thermal and fast frequency modulation as well, which makes them particularly useful for all applications requiring modulation. I want to thank you for your attention, and hope that you found this information useful. Please don't hesitate to either contact me directly at lut.maliki@oewaves.com or contact us at www.oewaves.com/contact. I look forward to any kind of a question or any feedback that you might have. And I wish you a very nice day. Thank you again.